Hi everyone, I'm Deep Nayak. I work as an applied scientist in the international machine learning team at IML. So far, you guys have understood what is the difference between correlation and causation, as well as why RCTs are a gold standard in evaluating any causal inference technique. Now we'll look at the different types of treatment effects and what are the different ways to identify them, as well as the different assumptions that go behind the different kinds of effects that exist in causal inference. So before starting with the formal definitions, let's take a quick look at one of the examples that will set up the intuition behind the different types of effects that we are eventually going to look at. So let's say we want to answer a very simple question of whether an internship leads to higher salaries in the future or not. Another way of putting this would be whether a temporary paid job raises the earnings in later stages of the career or not. So a very basic way to kind of get an answer to this question would be to do a survey among the people that actually have a job right now and look at the different subsets of our survey group, right? So we'll basically look at some people who have actually done an internship in the past and another subset who haven't done an internship in the past. When we do such an analysis, we basically assume that a lot of the underlying factors behind our survey group remain constant, which is very unlikely. So there can be multiple factors between our control and our treatment group that actually dictate the final answer that we get for our question, right? So for example, if we just do a simple survey and we compare groups who did an internship versus who did not do an internship, we'll most likely see a big difference in their prior year earnings as well. And at the same time, we'll also see a difference in the age groups, probably also see a difference in the marriage status, and also see a difference in like whether they hold a high school degree or not. So whenever these differences exist in our survey group, and let's say we get an answer from that survey group that one of our groups, which is the control, which did not have an internship, actually has lower salaries as compared to the group which has done an internship and has higher salaries, can have multiple answers, right? Maybe it's because the prior year earnings for the treatment was higher, or maybe the age group of the treatment was lower, right? So there can be multiple reasons whenever we do a survey of this sort, and that's why the answer that we get usually is not very reliable, or cannot basically answer the question of whether the internship led to the higher salary or not. So, as we have discussed earlier as well in the last module, the best way to answer such questions is to essentially have an RCT. So, there was an RCT of this sort that was conducted a while back, where around the 1970s, where what was done was that they took a bunch of people who were jobless for a long time because of various reasons and split them evenly into two parts. And this was done randomly, so there was no condition that was applied in picking people who were put in the treatment or who were put in the control. And after this random split, they picked a group of people and basically gave them a temporary paid job. And the other subset was not given a temporary paid job. And then their earnings was then evaluated in 1978 to basically see if the treated group who was given this temporary paid job actually had higher salaries or not. So this entire setup relies on the framework that we do a coin flip for deciding which person will enter the treatment or the control, right? So there's no conditions that we apply on this choice, and hence the decision of whether a person goes to treatment or control is random at best. When such an RCT took place, the overall finding was that for the group who actually were given the temporary paid job, we saw higher, around $1,700 higher salary as compared to the group who were not given a temporary paid job, right? So as we have understood earlier as well, let's say that this is the target that we are looking for. This is the value that we want to come up with which is around 17 or $1,800 of higher earnings by people who are given this internship, right? Uh, Now the question is, even if we know like this is the number we want to reach, what does this number actually mean or represent, right? And why is it that the survey group is not able to reach that number, right? So uh, when we are actually doing like looking at this survey group setup where we are just asking different people with a job right now of what their earnings are and then applying a condition on internships, we essentially remove the concept of randomizing our data set, right? So whenever we pick people in this manner, we essentially look at the estimated value of y, which is the outcome in this case, which is essentially the salary that people have when they had an internship, given that they had an internship, and we subtract the estimated value of the outcome, given that they do not have an internship, right? And let's say that our survey group estimate comes out to be around negative $8,400, right? So what this essentially says is that with our survey group, basically from our observed data, we are saying that people who actually had an internship saw lower salaries or earnings. Whereas from our RCT, which was randomized and which we know for a fact that is a better estimate, says that having an internship actually gives a higher salary, right? So we now have two data points, and we know one of them is a better estimate because of the randomization, but we don't know why the observed data is actually giving us the incorrect value. Why is it telling us that having an internship actually leads to lower salaries, right? So we'll try to answer this question mainly in this entire section, and we'll look at different ways to actually use the observed data to come up with a number that is very similar to the RCT, right? The main challenge with an RCT is that it is very expensive in nature. So, for example, even if you consider this RCT, it involved dividing people into two groups and then making a group get some internship and making the other group not get any internship. So, it's difficult to administer such RCTs. And if you think about the real world, for example, at Amazon, it would cost us a lot of money because let's say if you're deciding whether a customer should be given a coupon or not, there would be a subset which would be given a coupon, and the coupon will have some monetary value against it, which will cost Amazon, right? So running such RCTs is usually quite expensive, and usually the survey group setup is what is very readily available. So we need a way to match the result that we get from the survey group with the result that we are getting from an RCT, so that we can come up with robust estimates even without the need for an explicit RCT, right? So quickly coming to what we are talking about overall. So the concept that we are trying to explore here is the treatment effect. So the idea to kind of approach this question is divided into three parts. There are three quantities or three concepts that we should keep in mind whenever we are approaching such a problem. They are called the estimand, the estimator, and the estimate. So the estimand is basically the quantity uh, or like the question that we are trying to answer, right? So in the example that we were just looking at, it would basically say that we can basically say that we are looking at uh, the quantity or the increase in salary due to an internship in the past, right? We are looking at the effect of this intervention, which is giving an internship, on the final outcome, which is the salary of a person. Now, since we want to estimate this from the observed data, there are various techniques to do it, right? A simple technique that we have used is just subtracting the average salary you are getting from people with an internship minus the average salary you are getting from the group of people who did not have an internship, right? So that is one way of coming up with a number for that question that we want to answer, right? So that technique is called the estimator, which is basically the procedure that we are using to turn our data into one single number. and the estimate is basically the final number that we are actually coming up with, right? So uh, as I was mentioning, you have a question that you want to answer, which is basically the estimand. You have a technique of answering that question, which is basically the estimator, and you have the final answer that you get from it, which is basically the estimate. So if you think about it, in any setup where you are working with observed data and you have these three concepts, there are uh, two different ways of going wrong about it, right? The first way is to basically ask the wrong question where you don't know what you're looking for and you are actually asking the wrong question for the quantity that you're actually looking for. And the second way to be incorrect about it is basically use an incorrect estimator or rule, right? So essentially, you use a technique that is very biased or has some problems that will always give you the incorrect answer, no matter how correct the question you ask is, right? So if you just look at this diagram, it basically says that this is like the final quantity, the estimand that we are looking for. If we use an incorrect rule and if we pass our observational data to that rule, it will basically give us an output which is way off the final result that we are looking for. And if we use the correct procedure, we can probably get very close to the final outcome, although probably not as accurate as an RCT, but still very close to that number, right? So our goal with this module is to understand what questions should be asked in different scenarios and what's the right way to get an answer for those questions, right? So now coming to like the formal definition of different types of effects that we usually look at, right? So the question that we had very recently asked, which was basically what is the gain that you get in salary because of an internship, that is a form of ATT, which refers to average treatment effect on the treated. So if you think of the entire population, if you look at this grid, it basically represents, so every point basically represents a person, let's say, who had the potential of getting an internship or not getting an internship, right? So let's say this is our observed data. Now there is a subset treated where we basically have people who actually did an internship, and there is another subset control which has the set of people who did not do an internship, right? So when we say we want to look at the incremental impact of having an internship, and when we say we are looking at ATT, we are basically averaging out the effect, or basically averaging out the salaries that you are getting for the treated. And we are also subtracting the case where the same people did not get an internship, right? So the problem is that in causal inference, we usually look for counterfactuals. So Y0 in this case would actually be a counterfactual. A potential outcome that is actually never observed in the real world. But ATT essentially represents that hypothetical scenario where you just take the treated, you subtract the outcome that you are getting when they were treated versus when they were not treated. And then you basically average out that value, right? So that is the ATT that we were looking for in the previous question. Another very simple effect that people usually are interested in is the ITE, which is the individual treatment effect, where we basically say that for a given individual, what would have happened if they got some treatment versus when they did not get the same treatment, right? This is again very difficult to calculate because we cannot look at a scenario in the real world where the same person, let's say, is given an internship and also not given an internship, right? Those two are contradictory statements. Um, then we have AT, where we basically look at the entire population and we say that, okay, if you average across all the people who had an internship or did not have an internship, what will be the average treatment effect that you get across all these people, right? So that is ATT. Similarly, we have ATC, which represents the average treatment effect over the control. So that basically says that if you only consider the people who are present in the control group, again, what was the difference in the potential outcome when they were given an internship versus when they were not given an internship, right? And then we average out the entire effect. This is again a hypothetical quantity because in the control where we do not actually administer the treatment, or where people do not have an internship, we cannot get a scenario where they actually do have an internship, right? Um, and lastly, we have Kate. So Kate is an interesting quantity, and it also leads to some of the techniques and questions that we'll ask in the later slides. So Kate essentially is conditional average treatment effect. It basically asks the question that what would be the average effect of having an internship, let's say, given certain pre-treatment covariate values, right? So what I mean by that is, given some condition on some characteristics of the people who are participating in the like the internship program, uh, what is the treatment effect just for that particular subset, right? So to dive deeper in Kate, right? So let's say, if you look at this formula, you'll basically see that we are looking at the difference in the potential outcomes given some values of X, right? So what we essentially mean by that is we can look at it like in two ways. One is that we hold the value of X constant. So what we mean by that is, let's say, if we have one of the values of X as married, whether a person was married or not before participating in that experiment. Um, and let's say there are different distributions of this married, right? So for example, we have higher percentage of people who are married as compared to the percentage of people who are not married. So one option is that we look at only the subset where people are married. So there will be no effect that marriage has over the final outcome, right? We are essentially removing the effect of marriage. If we are only looking at people who are married, and then we are looking at subgroups in that slice where people who are married got an internship and did not get an internship, then the effect that we'll find from that subgroup will be free from like the effect of marriage, right? And we can do a similar slicing at the not married group as well. So if you only look at the not married group, like that small slice, and then look at the two groups, you'll get a different average treatment effect. So when you create such slices, you essentially say that you're looking at Kate, or the conditional average treatment effect. Um, Another way of basically looking at Kate is, instead of just looking at that small slice, let's say we look at the entire population and then we balance the mix, right? So, for example, if married people had a higher concentration, let's say 60% of our group was married as compared to not married, which was 40%, we'll try to reweigh them. So we'll give less weightage to the married population and more weightage to the not married population, such that both of their effects are kind of balanced, right? That is one more way of looking at like the Kate value. So we essentially say that since we are balancing the marriage proportion, whatever value we get out of it will be free from like the effect of marriage, right? So that is one more again way to compute Kate. Now, similar to marriage, there can be other factors as well, like other value, other columns in X that can actually impact the final effect, right? So, for example, marriage was one example, but schooling is another, right? And age is another one. Uh, and as I was mentioning, like you can either like take a slice and then look at the Kate value, or balance the entire mixture and then look at what the final value is that you're getting. So now that we have established that, okay, we cannot always do an RCT and we will have to find ways to work with observed data, or like data similar to that surveyed group, and then come up with estimates that are very similar to RCTs. And now we also know what are the different questions that we are answering, right? Are we looking for the ATE, or are we looking for the ATT, or are we looking for Kate, right? And what are the different types of like answers we get out of them. Let's now quickly look at some of the problems that we can run into when we are trying to work with these observational data sets to come up with these estimates, right? So the very first problem that we can come up with is the selection bias, right? So what selection bias essentially means is that whenever you get observed data, there is some inherent bias in that observational data itself, right? So, for example, you have some observational data, and there are two groups that you're dividing that data into, let's say the survey groups, where one had an internship, the other one did not have an internship. The groups can be dissimilar to begin with. As you were discussing, maybe the earnings can be different, maybe the marriage share can be different, right? The other problem that can come up with your data set is that, as we were discussing, there are ways to look at Kate or like subsets of your data set where you get like balanced representations or like the balanced average treatment effect. An analyst, or basically us who is looking at the data set, can make mistakes or select incorrect variables when they are looking at these subsets, right? So marriage or age was one of the variables that we considered when balancing that mix, but maybe we pick some incorrect variable that actually does not have an impact on the final effect, but because of our choice leads to these effects, right? So there are like two kinds of such problems that can occur, right? So we'll quickly go over how these problems look in the real world and how we can kind of mitigate them. So, if you look at the naive estimate that we originally started with, which is basically just take the average salary of people with an internship and average salary of the people without an internship, that can actually be divided into two parts, right? The first part is the ATT, which basically says what is the incremental salary you get after giving people internship. And then you have this other component, which is essentially known as the selection bias, right? Where you are basically saying that for people in the control, what is the outcome that you are seeing um, uh, when they did not have an internship versus the same in treatment, right? So when you decompose it in this manner, we basically see that there are different covariates that we were not able to balance on, right? For example, earnings, married, etc. And as you balance each of these covariates, we'll essentially get a lower bias in our final outcome. So it will be more and more closer to the like the RCT data that we had, right? Or the RCT ATT value that we had, and this selection bias term will essentially be zero. So now our goal is to essentially turn this term to zero, or basically remove as much bias as we can from the final effect that we are getting, right? So one basic question that people might ask is, let's say we consider all possible factors that can affect this impact, right? So for example, marriage, age, previous education, these are three factors that we can think of. But what if we consider everything that's possible, right? What if we also consider cases where people had a job, or people were jobless for 2 years or 3 years before this experiment took place, or we consider n number of variables that we want to balance on, right? Maybe if we consider enough variables, we would be able to remove all possible biases, right? um, Now, there is a problem with this approach. First of all, as you guys know, like it would be very difficult to think of all possible scenarios or things that can impact a particular outcome. But when you do end up doing that, you, let's say, think of exhaustively what are the different things that can affect the final effect that you're trying to calculate. You can run into two problems, right? So one problem is basically, let's say you are considering some factor and you run into a mediator, let's say. So a mediator, as you guys have learned before, is basically a variable through which the treatment has some effect on the final outcome, which is earnings, right? So if you end up balancing for the mediator, you will essentially remove the effect that the treatment has, because that is the only path that the treatment has to reach to the final outcome, that is through the mediator. And if you're saying that you'll hold the mediator constant, that will remove any kind of effect that the treatment would have on the outcome. So the final answer that you get will actually be incorrect, right? So for example, in this scenario, in the running example that we had, if we just add a condition on the mediator that let's balance the mediator, or let's say the mediator in this case would be what is the monthly salary that you're getting, right? That's So if the internship has a positive impact, it will have a positive impact on the annual salary as well as the monthly salary, right? So if you're holding the monthly salary constant, then you'll basically not see any impact of the internship on the final outcome, right? The other problem that you might run into is the collider problem, right? So this is another kind of selection bias that can come up, where you're basically saying that there is one variable that is affected by both the treatment as well as the outcome, but you are essentially holding that constant, right? So when you do this, what you essentially do is you create a backdoor path, as you would have learned earlier, and you end up creating this fake path from the treatment to the final outcome, because you have assumed that there is some effect that treatment has through the collider to the final outcome, right? So when you condition on the collider, you end up creating this backdoor path, and you again get like a very incorrect estimate that is very far off from the RCT data, right? So these are two problems that can happen when you are selecting different controls or different things you want to condition your final effect on, right? Now there are some set of assumptions that we have to work with whenever we want to identify this effect from observed data. So when you are working with an RCT or like any data from an RCT, you can be free of these assumptions because the randomization kind of takes care of a lot of these problems. But in observed data, you have to basically make sure that these assumptions are satisfied so that the final effect that you get is robust enough, right? So uh, one condition that we just looked at was like selecting the right controls or the right values of X that you want to condition on. The second is unconfoundedness, right? So what this assumption basically says is that given all the possible controls that you have identified, there is no other hidden control that can impact the outcome, right? Or essentially the outcome as well as the treatment. So, as I think you have already discussed earlier, such things are essentially called confounders. So, if there is a confounder that you did not account for, that is present in your observed data, and that is not a part of the subset X that you're conditioning on, it as the effect of the confounder increases, there will similarly be like a bias that you're adding to your final estimate, and it will be very different from like the actual ground truth that you have. So this is one assumption that we essentially have to fulfill whenever we are working with observed data, that we have no hidden confounders. The second assumption is called the positivity assumption. So the idea here is that let's consider one X, which is basically age, right? And let's say you have people from age 25 to 50 in the control, but people from age 25 to 100 in the treatment, right? So for the subset of 50 to 100 that's present only in the treatment and not in the control, you'll have nothing to compare against, right? So what you end up assuming in these scenarios is that for any person who is age 60 or 70 or anywhere from 50 to 100, right? The effect is very comparable to someone who is aged between or less than 50, right? From 0 to 50. So that is a very strange assumption if you think about it. We are essentially saying that the effect of the treatment on elderly or like people with a higher age is the same as the effect that you get on young adults or children, right? So the main point of this assumption is that whatever values of X you are working with in your treatment should also be present in the control, so that you have comparable groups, and whenever you are estimating the effect, it is measurable with like a subset of the data that's present in treatment as well as control, right? What happens is if you don't have this overlap, as you can see here, there are these red regions that are created where some data sets or data points are only present in the treatment or the control, and we end up getting a very biased estimate if the data set looks like this, right? So the end goal should always be working with a data set where you have as much data as possible in the green region, where you have some data in the control as well as in the treatment for all possible values of X. And if you think about it, you'll usually not work with just one X, you'll work with multiple like columns in X, which is basically age, marriage, previous earnings, etc., right? So one more assumption that we need to make sure is present in our or is satisfied by our data set is basically called stable unit treatment value assumption, right? So this essentially says that whenever you are considering two units or two people, the effect of giving one person an internship will not leak into some other person who was not given that internship, right? So in our very crude example, let's say motivation is one factor we have not considered. And let's say there are two friends and we are giving internship to one of the friends. And let's say the other friend who was not given an internship is actually motivated by this friend and actually increases the pace at which they are searching for jobs and ends up getting multiple offers, right, through that process. So in this example, there is some effect that us giving internship to one of the friends has on the other friend as well, right? If that is the case, we cannot assume that there is no dependence between two individuals who are given a treatment and not given a treatment, right? Whenever there are any kind of spillover effects or some leaks, like I just explained, there can be some biases that are introduced in our final effect, right? So this is again something that we need to make sure does not exist in our data sets. In the real world, what happens is you usually do not satisfy all of these assumptions perfectly, but you always need to show your sensitivity or like the sensitivity of your proposed approach to these assumptions. So let's say I am working with e-commerce data and I know that giving one customer a coupon will definitely affect some other customer who was not given a coupon. Maybe they look at this customer and increase their spend in hopes of getting a coupon, right? So such effects can exist in the real world, and maybe we build models by assuming they don't exist. But once those models are built or once those solutions are in place, we need to kind of show how sensitive our approach is to these effects. So maybe we'll show or compare the effects that we are getting from our method or from our model in both of these scenarios, and then show how different they are or how they vary whenever like the percentage of such cases is increased or decreased, right? This is kind of essential to gain confidence in any kind of solution that we propose in causal inference. And it's true for any kind of effect that you want to estimate, whether it be 8 or K8 or ATT, etc., right? So now that we have a good understanding of what are the different assumptions we would want the underlying observed data to kind of hold, and what are the different effects that we can look for, we will now come to how we will actually do that, right? How do we recover that number that we are looking for, or how do we actually estimate the effect? So now we'll cover the different estimator techniques, right? So a very basic technique that actually works quite well for smaller data sets is essentially to have stratification in our data set, right? So the idea is that let's say you have just one variable, which is age, which is like an external factor that can impact your final outcome. You would want to balance or like account for age, right? So since age is a continuous variable, what you can end up doing is that you can create bins, right, of different age groups. This process is called binning, and the idea is that within every bin, you would assume that people are very similar in behavior to each other, right? So, for example, people aged from 16 to 24 would have a very similar effect, a very similar outcome value as compared to people who are aged from 40 to 56, right? So, ideally, the smaller your bin size is, the more accurate your final results would be. And in the very extreme case, you'll basically have bins for every possible age value, right? For example, age 16, age 17. The only challenge with smaller bins is that you should have enough data in your data set to kind of support the estimates within each bin, right? So the main reason for that is once you have created these bins, you'll basically estimate the effect where you are just subtracting the average of the group from the treatment from minus the average from the group from the control. So you get some effect values from each of these bins, and then you basically average them. You take a weighted average basically by um, weighing each bin by the number of samples that are present in that bin, right? And you essentially get like the overall ATT estimate, right? The problem is that if your bins are too small, your estimate would probably be very accurate, but your bin size, or for example, the number of people in every bin would be very small. So you can actually get results that are way off when you're actually averaging across using that technique, right? But on the other hand, if you have very large bins, what happens is you can have problems with the assumption that you're making. For example, if you have a bin from age 16 to age 56, the assumption that their effects is very similar may not always be true, right? The another problem with very small bins is that you probably won't have any data point at all in some of the bins. For example, you have no data point for age 17, but you have data points for age 16 and 18. You will get values that are very off in that particular bin, right? So um, that are some problems with stratification, but overall, if you think about it, this approach works well for like smaller number of x values or smaller number of things that you want to condition on. But what happens if you actually go beyond one or two x, right? So another technique to actually do the same balancing is basically matching. So the idea here is that for every data point that you have in your data set, and let's say you are looking at two axes where you have age and prior earnings, you would basically try to find the nearest neighbor of that particular data point, right? The idea behind it being that you don't have a direct counterfactual for that particular data point. You don't know what would have happened if they were given an internship or not given an internship. And that's why you basically look at a data point that is very close to it with respect to prior earnings and age, right? So maybe in the control, you find a data point where the earnings is very similar and the age group is also very similar. And the only difference then is basically whether they were given an internship or not. Uh, so the difference in that case will be very accurate, or basically give you like a number which will be like the impact of just the internship and not the other factors. Now, what you do essentially then is that you average out the value that you're getting using this technique across all data points in your data set. But as you would have again noticed, this is computationally very expensive, and in this example, we only showed you like the process of doing it with two axes, which is earnings and age, right? But ideally, you would have like a much higher number of things that you want to condition on. So if you see, even in this example from our data set, or like the internship example that we are working with, when you condition on just these two factors, the final outcome that you get is still very off as compared to like the ground truth that you had from the RCT, right? So there is still something that we are missing out on, and that's mainly because of other factors that we have not conditioned on. So, one more thing to kind of understand or get intuition on in this process is the similarities between stratification and matching. So, if you think about it, we are doing very similar things in both of these procedures, right? They are based on the same two conditions. Essentially, both assume that there are no hidden causes or hidden confounders in your data set, and they also assume that you have enough overlap. So, whenever you are doing matching, you have data point that is very similar or close to your other data point from the control group. And similarly, in stratification, you are basically assuming that in a bin, you have enough data points from both control and treatment, right? So they are based on the same two assumptions. They are just two different techniques of getting like the final estimand that you are trying to get, right. But as I was mentioning, the problem with both of these approaches is basically the number of covariates that you can condition on. They work well for smaller number of covariates, but you will have to think of better techniques if you have a large number of covariates or confounders, right, that you want to condition on. So one important thing to keep in mind, as I was mentioning, was like the number of covariates. So not just the number of covariates, also like the number of bins that we end up creating, right? So here is just like one example of how we can actually run into problems very quickly when we are working with a very basic technique like stratification and the other technique, right? So the problem with these two approaches is that if, let's say, you consider only three different levels. So for example, even for age, you are creating only three different bins, and what you then do is basically you select a value of p, which basically denotes how many points they are actually matched on, and then scale the value of p, right? So the value of p will basically be exponential. So as you increase the value of p, which is basically how many traits the data set is actually matched on. So traits here is basically age or your earnings, etc. The As you see, the number of cuts that you are making to the data set actually goes up exponentially. So just with p equal to 4, which where you're matching with matching across four different confounder values or traits, you will end up creating 81 different cell or 81 different small little buckets, and you want to fill each of these buckets with enough data points from both treatment and control, right? So if you see, with just four different traits from our rudimentary data set that I had actually introduced earlier, we are getting only 14.8% of the cases where or 14.8% of the cells which contain data points from both the groups, right? From both control and treatment. And this actually becomes worse as you increase the value of p, and it becomes worse very quickly. So at p equal to 6, that 14% number actually goes down to only 4%. And at p equal to 8, it actually goes down to only 0.6%. So now only 0.6% of the total buckets that you created or small pockets that you created actually have data from both control and treatment. So this is called the curse of dimensionality, where basically these techniques run into problems very quickly if you introduce more number of confounders that you want to condition on. And that's why there are other techniques to actually handle such problems, right? So one such technique is basically the propensity score. So the very basic idea behind this is, instead of like explicitly matching or creating buckets in your data set from different confounders, let's say you select your set of confounders or like the correct controls that you have decided, and then you train a model that will basically predict how likely a given data point is in your data set to fall in the treatment cohort or the control cohort given these values of x, right? So this essentially is another way of saying you want to calculate the propensity of every data point of falling in the control group or the treatment group. So it's quite well proven that when you actually build a model where you predict this using just the confounders, you actually get like a single number between 0 and 1, which accounts for all the values that the underlying confounders can take, right? And now all you have to do is, for any new data point, you'll just pass it through the model and get a propensity score. And then you will have like a propensity score for each and every data point that you have in your data set. So this is one way of kind of getting around the dimensionality problem. But one thing to be very careful in this technique is that when you're actually building a model of this sort, you can actually very easily get in a trap where you are trying to optimize the model to perform better in terms of classification, right? So as I was mentioning, if you want to get a propensity of basically how likely the data point is in falling in treatment or control, you will end up building a classification model, which will basically classify whether it should go in treatment or control. And then you'll add up adding different variables in your data set, which will improve the performance of the classifier, but will actually not give you very useful or meaningful propensity scores. So for example, in the very good classifiers, a lot of your final output will be kind of separated or concentrated towards 0 and 1, right? um, And when that happens, it's not very useful for your causal inference techniques, because now for every data point it's either very close to zero or either very close to one. So now you don't know if you want to match or pick two data points that are very similar, which ones you should actually pick, right? Because either it's very close to zero or very close to one. We'll also see another problem that this causes in some other, like in another technique that we'll discuss later. But yeah, this is one problem that happens. Now, another technique that's very popular is basically inverse probability or propensity weighting. So the idea here is that for a data point that is actually very close to your decision boundary of falling in the treatment or falling in the control, it's actually a very good counterfactual, right? So for any data point that's very close to that decision boundary, you ideally want to have a higher weightage or a higher importance in your data set, as compared to some other data point which was very unlikely to fall in the treatment and is just like highly likely to fall in the control, right? For those data points you would actually want to give lower importance, because those do not act as very good counterfactuals for your scenario. So as you'll see in the plot here as well, we basically have propensity score on the x-axis, and we basically want to give more importance to the data points that are close to the zero point 0.5 propensity score, right? And less importance to data points that are very close to zero. Now, if you have a very good classifier, you'll have a lot of data points very close to zero or very close to one, which is not even there on this graph, right? And when that happens, you won't have a lot of data points which you want to give importance to. So in this part, if you can actually see, when you move around and do not account for like a lot of these data points, you'll see that like a very small percentage, which is like 7%, 7 of like the total controls that we have identified, account for almost 80% of the weight that you are giving, right? So essentially, you want to build a good propensity model that is not necessarily always like a good classifier, but still gives you like good propensity scores that you can match on, or that you can weigh samples on, right? So using this propensity score and basically using this formula that you see, where you are giving more importance to cases very close to the decision boundary, you can actually come up with this estimate of ATT, which basically accounts for like different confounders that you have conditioned on, right? And as I mentioned earlier, since you're weighting by this E divided by 1 minus E, it basically weighs like the different scenarios where you have a very highly unlikely cases that you don't want to give a lot of importance to, right? Um, then since now we have like this propensity score, what we can also do is that we can kind of trim the extreme weights that we get, right? So for example, if we already know that there are some data points which have very high propensity values or very low propensity values, and we know that the formula that we are using here will kind of blow up if the value is very close to one or very close to zero, right? What we can do is we can basically trim our dataset to not have values or not have data points from those parts, like, and or the other technique is basically we basically cap the weights to these values, right? Happens with this is we get more balanced or like stable estimates that are not way off because of this exploding propensity problem. But yeah, that's one way of essentially handling that extreme weight problem. So, in summary, what we basically saw is that we have two different techniques, basically matching and weighting, and there are like different kind of estimates that we can get from these techniques, right? Uh, uh, Ideally, like we would want to look at the data set to understand which one is the right one to use. But usually, what happens to be the case is that we have a lot of confounders in the real world, and that's why a propensity model is probably a better way to go about it, provided that we choose the right confounders to condition them on, right? Now, what we saw so far was basically just a way to get the propensity of a particular data point falling in control or treatment. But there is actually another technique that we can use to kind of maintain this balance, which uses regression, right? So instead of building a classification model where you're trying to get a probability, what you can also do is take confounders as input and build a regression model which will directly try to predict the salary or earnings that you get based on these values of X, right? Um, so what happens here is you have some estimates from you basically train regression models for both your control set and your treatment set, and then you have models which will basically give you any counterfactual value, which will basically tell you that what would have happened if you passed like some data point from the control to the model that actually estimates the effect for the treatment. What would have been the salary, and then you basically subtract these values for all data points and take an average. So that gives you kind of like an AT value using like a regression model, right? But one problem with this approach is that if you think about it, um, in the propensity model, there were cases which were highly unlikely, which used to get like very high weights or very low weights. And it would also show up in the final estimates, right? Which would be very off because of this higher weights. With the regression model, that actually does not happen because since you have built, we usually build like linear regression models over here. The model actually extrapolates in the regions where it does not have data, right? So, for example, in this case, let's say we have treatment data but no data in the control group, the model will still come up with a estimate that is very close to like the all the other data points, or like the line that was extrapolated from the other data points, right? And it runs into the same problem that I had mentioned earlier, where you basically assume that the effect of this unseen data point is very similar to the effect that you are getting across the other age groups, right? So this is just one problem to be mindful about whenever we are working with such regression models. It is one more technique to actually help you with scenarios where you have a lot of confounder values, but we need to make sure that there is sufficient overlap across all the confounders that you are considering. Otherwise, you'll get end up in scenarios where your data is extrapolated and your estimates are actually biased, where for example, you see here that the regression number is actually way off than the actual value that we are getting from the RCT, right? um, One more technique that's quite popular is basically doubly robust estimation, right? So far we have seen two different ways of handling scenarios with multiple confounders. One is the propensity method and the other is the regression method. One acts like a classification model where you are trying to estimate the probability or propensity of falling in the treatment or control. The other directly estimates the final outcome through a regression model. What you can now do is kind of combine both of these models, or use both of these models to come up with estimates that are much more robust, right? So the idea with doubly robust estimation is very nicely put through this equation, right? So what we essentially say is that we most likely would want to rely on the output from the regression model. But in cases where the regression model is incorrect and there's some residual or some bias that's present in the output of that regression model, that bias will be weighted by the propensity model that we have learned, right? Um, so the guarantees of this doubly robust estimation is that if you're not using a model for any one of them, and if you have the true value, so for example, if you have the true value of the propensity, but you are actually estimating the regression, or like the this mu hat value, you'll actually get an outcome that's exactly what the RCT would have given you, right? And this works in an either or setup. So essentially, if you're saying that you only have like the outcome model, which is this mu hat value, that's the very accurate, and you have a propensity model that's not very well learned, even then you'll get the right outcome, right? Only in the scenario where you have incorrect outcome model as well as propensity model, you'll get like a estimates that that's very far off, right? That's completely wrong from what your ground truth is. But in all other scenarios or combinations, you'll basically end up with an estimate that's very similar to the ground truth. And even in cases where you're using a model for both of these quantities and they are very decently built, the bias term that is actually found in such models is actually a product of the error from both of these models. So it's highly unlikely that your estimates will be very far off, even when you're using well trained models for both of these quantities. So this is known as a doubly robust estimation, and this is kind of like the foundation of Neyman orthogonality and DML as well that you'll learn in the upcoming slides. But yeah, this is one more robust way of kind of coming up with the final quantity of interest. So in conclusion, we have so far like covered different techniques. So for the same example that I was using before, let's say giving an internship or not, and does it lead to higher salaries or not? We have multiple techniques now. We started with the naive comparison, which had a very high bias. Then we looked at some matching techniques, and we saw that they were actually doing better but not quite meeting the bar because they were not accounting for all the confounders at a given time. And then we looked at different propensity and regression methods to actually kind of correct for the remaining bias and account for all confounders when they are actually producing the final estimates, right? So we looked at the regression method, we looked at IPW, and we also looked at the doubly robust method that kind of combines both of these techniques. And we have been getting closer and closer to the ground truth with all of these techniques, right? So, in conclusion, like if you are working with a very high number, or in fact, even like a decently large number of confounders or controls that you want to condition on, you should ideally rely on propensity or outcome based methods. And if you have a way of getting accurate values for either one of them, the doubly robust method is the most convenient and the most accurate one out of all the techniques that we have discussed so far. So what we have learned so far basically covers like the different effect estimation techniques that are present and the different types of effects that you can actually measure from observed data, and how you can kind of set out different assumptions on your observed data to make sure that your effect estimates are very close to the RCT ground truth that you would have in place if you did run an RCT, right? So all of the techniques we have discussed so far are classical estimation techniques, but there are actually much more advanced DL based techniques as well that work with even higher dimensional setup and give you much more accurate estimates, right? So in the next modules, we'll basically look at the different machine learning techniques and DL techniques to actually come up with the same effect estimates. So thank you. Thank you for the session.